Okay, we have this integral here today from the Berkeley Math Tournament 2024 Calculus number 6. We have the integral from 1 to 36 of the square root of 3 plus the square root of x minus 2 dx. I did this problem about a month or so back, and we had an interesting suggestion in the comments from El Quese Hombre to do this with an alternative method using inverses. I don't know if it's really quicker because it's kind of a trade-off. It's still kind of messy, but it's more about the interesting method. I really like this method, and I've done a couple other videos on it. So let's take a look at this method using inverses. Okay, so we have this formula on the board to use on it. I derived this about a week or so back. It's just from integration by parts. It's not too hard to derive. I'll provide a link to that other video where we show how we get this. But what we're doing is, if this is our integral here, we have, we know our bounds. We have our bound, like our b value is going to be 36, our a value is going to be 1. We're calling this thing here our f of x, so it's going to be easy to get these values here. The question is, what about this inverse function here? How do we find that? Well, that's probably the hardest part of the whole thing. Let's just set this whole thing equal to y for our f of x. And then in order to find the inverse, all I need to do is solve it for x. So first what we'll do is I'll square both sides. So we have y squared equals square root of 3 plus square root of x minus 2. We don't have to worry about absolute value just because of our bounds on the x. This is always going to be positive. And then from here, I think what I can do is let's add 2 on both sides. So then from here, what I can do with this, we'll have y squared plus 2 on this side, but we're going to square both sides again because we have to get rid of all these nested radicals. So over here, we end up with 3 plus square root of x, but we're squaring this as well. Squaring this out, we're going to have y to the 4th plus 4y squared plus 4. And then here, we're just going to end up with 3 plus square root of x. Subtract a 3 on both sides. This is going away. And then we're left with just a plus 1 over here on the left side now. So we'll clean this up right here. And all we have left, we're trying to isolate x. And we have square root of x here. So all I'm going to do is let's just square it one more time. So it's a little tedious with all the squaring going on. But what that's going to do is now we've isolated our x. We'll switch sides, and now we have x equal to this thing. I just need to square this whole thing out, and let's see what we get. Okay, so now after multiplying everything out, adding everything up, collecting like terms, we have our expression. We just need to switch the variables, flip the y's and the x's, and we get an expression for our inverse. So for f inverse x, it's going to be x to the 8 plus 8, x to the 6, 18x to the 4th, 8x squared plus 1. So let me just clean everything up, and we can continue with what we found. Okay, so now putting our formula to use, before we can totally do this, we need our f of b and f of a value, with our f of x being this. So for f of b, where b is 36, I just need to plug 36 into this thing. So when we do that, square root of 36 is 6, plus 3 is 9, square root of 9 is 3 minus 2, square root of 1, this value is just 1. So this is going to be our f of b. And then for our f of a, we just need to plug in 1. So when you do that, square root of 1 is just 1. Square root of 4 is 2 minus 2. This is going to be 0 for our f of a value. So now we can just go ahead and plug in. So we know our b is 36 times f of b, which is 1, minus a. It doesn't really matter because it's 1 times this 0 here. So that's going away. And then here we're going to have an integral where the bounds are going to be f of a to f of b. So it's going to be 0 to 1. Of our inverse function that we just found, which is all this. And so this is kind of how these are supposed to work. This is kind of nice because we took this nested radical situation. Now we just have power rule with this integral. It's just that in this case, there's so many terms that we probably didn't save a lot of time. The inverse was kind of tedious, but in a lot of cases, if you can convert it to power rule, it's going to be faster. So now we can just go ahead and integrate and finish this thing off, just calculating. So what we're going to have, so what we have here is going to be 36 minus, I'll just power roll, x to the 9th over 9 plus 8 over 7, x to the 7 plus 18. See, it's kind of a mess, but it was kind of a mess the other way too, so I'm not saying it's a mess either way just because of the nature of this problem, I think. And we just need to evaluate this from 0 to 1. Well, the bounds are pretty nice because 0, everything's going to be 0. You plug in 1, and what's going to happen, all these x terms really go away. I mean, this one's going to be a 1, but really we just end up with all these fractions. This one's going to be like 1 over 9. So let me just clean this up so we can see exactly what we're doing. And from here, all you need to do is get a common denominator, add all these up, subtract it from 36. And for my final solution on this, we get 8,656 over 315, and that's it. Now, one other thing before I finish up that's kind of interesting about this is looking at the graph, because it kind of gives us a visual representation or a visual way to think about this formula here. So just a very rough graph over here to the left. I think it's actually a little better to look at this than Desmos in this case, because in Desmos, it kind of spikes so fast that it's hard to look at. But if this one on the right, this is going to be like our f of x function going from 1 to, 36 is going to be out here somewhere. And so if we were just integrated straight away, we're getting this area under the curve here. Now, if you take the inverse function, it's going to be reflected along this x equals y line, or y equals x right here. So you're going to have something like this over here. So because these two curves are just reflected, this area up here will have the same exact area as this over here. And we just need to kind of calculate it with all this stuff on the right. You'll notice when we actually calculated this piece right here, this value was 36. What that corresponds to is if you did this, if you created, it's going to look kind of like a mess, but if I tried to create a rectangle, this width right here is going to be 1. If this point up here is 36, this totally misshapen rectangle is going to be width 1, height 36, so the area of it's going to be 36. So if this whole rectangle, the area is 36, what we did is we subtracted off this integral here, the inverse function, from 0 to 1. So what we did is we took the 36 and we just subtracted off this right here. But you'll notice subtracting this area from the whole messy rectangle just leaves this area here, which is the same as this right here. So I don't know if you can follow that whole mess, but it is pretty intuitive when you take a look at it and you line it up with this formula right here. Okay, that's it for today. Thanks everyone for watching. Have a good day.